Good morning, everyone. Today is April 29th, 2017. And this is the John Chappell Natural Philosophy Society Saturday morning science chat. So for today's chat, I thought we would just do a specific topic, which is how does the magnetic field work? And I picked this topic because I think it's something that it doesn't generally have a very good explanation. I don't think the mainstream has really an agreed upon explanation. In fact, this is one of the three forces that I don't think the mainstream can adequately explain. So we have like the electrostatic force, we have gravity, and we have magnetism. And I don't believe that there's a really good explanation for how these basically mechanically work. I mean, the question is what causes particle A to move towards particle B and to create the forces that it does. So, and that's what we're here to talk about in the science chat, are things which don't really have good explanations, or things that other people have explanations for. So I want to take a survey first and find out, is there anyone here who has a pet theory about how magnetism works? And so I have one theory about how magnetism works. But I don't think that I've encountered very many people who are willing to volunteer when asked the questions, you know how magnetism works? They go, yes, I've got a theory. Let me. So I was wondering, do people here on the call have any strong opinions about how magnetism works? Just first of all, this morning, find out.
I have an idea, but then you have to go to dive a bit in field equations. In fact, quaternionic differential calculus explains quite well what part of change is generating magnetism. It's the part of change that is defined by a curl. The magnetic field is a curl of a general field.
Well, my problem with explaining magnetism with equations is that equations don't attract. Equations don't repel. Equations generally explain the empirical observations. I mean, but if you're going to stick with the empirical observations, then you can just use Maxwell's equations and say that that explains magnetism.
If you
so I think
that,
first of all,
if you put that,
I think that's
then I have to hook off. I think
pardon?
Part of magnetism is indeed mathematics, and it's physical reality. It's following for a part this kind of mathematics, and that you can observe. But the what's behind it are these differential equations that are Maxwell equations. Maxwell equations are differential equations.
And once again, those would explain the empirical results.
Well,
but
how do you?
How do you want
to, well, give it a try, then I'll listen.
Okay, well, but that's certainly one approach. I mean, there's approach. So we'll keep that in mind as one approach, which is kind of a mathematical approach. But my question would be, then why can't we just use Maxwell's equations? Why doesn't that explain how magnetism works?
Franklin, Duncan Shaw calling. Do you hear me?
Yes, we hear you.
Okay. Thinking about Maxwell's equations and the paper that he wrote in about 1864 that sets them out, in that paper, he also sets out his vision physical vision of the equations that he has in that paper. And he has a number of things in it that I think are important. One, he bases what his equations on there being a substance called ether that exists, and upon ether having elasticity. I happen to think there's a lot to what he says, and the fact that he said it and that this underlay the equations that have stood the test of time is an important factor. Translating that into the mechanics of magnetism is terribly difficult. There's no question. And as you said when you opened, there's still no real accepted mechanical theory of what constitutes magnetism. And one other thing, I agree that equations are necessary to describe. They're a language unto themselves. But at the same time, I think it's necessary to have a vision in one's mind of what actually is happening mechanically. And that's another thing altogether. And I do not think equations give you that. It's your imagination and ability to see things in your mind. I'm glad you raised the subject because I'd like to hear different ideas on what mechanically constitutes magnetism. Are there cells? Are cells? Do they twist? Do they turn? Is it a pushing motion rather than a attracting or pulling motion? It seems to me those are key questions, and I would be very interested in hearing what the participants have got to say on that.
Let's see here. I just looked up. Let me share this with you guys. So Maxwell definitely had a sense of how he thought things worked here. Let's see here. Where is my? Here. See if I can share that. Okay. So this is the Wikipedia on Maxwell's equations here. History of Maxwell's equations. And let's see here. Now basically, let's see here. We have the basic magnetic equation here is that Gauss's law? No, it's not Gauss's law. That's which is the law that describes which is that the magnetic field is described by B, and you have to take the cross product of E, which is the electrons. I believe that's this formula here. F equals Q, E plus V cross B. And that in itself is kind of hard to understand. So this equation says that the force that a charge feels, which is Q, so if you have a magnetic field and you have a charge, that is proportional to, I believe, the charge. I'm not quite sure what E is, but the V is the velocity of the charge, and it's the cross product of the magnetic field. Now, what's strange about the magnetic field is that it only exerts a force if the charge is actually moving. If the charge is stationary in a magnetic field, the velocity is zero, so the force ends up being zero. But not only that, you take the force is actually in a 90-degree direction, perpendicular to both the direction of the electron and the direction of the magnetic field. And this is usually visualized by using the basically the right-hand rule. And that's a really another complicated thing to explain. Let's see here. Let me see if I can explain. So if I have my fingers here, so I've got my 3 fingers. I got my thumb, I got my first finger, I got my second finger. So the deal is that if the electron, well, let's say if the electron is heading this way and the magnetic field line is heading this way, so that forms like an angle, right? And this can vary. But now the force actually is described by my thumb. So the force comes out that way. So this is really weird that the electron is going this way, the electric field is going that way, but the force is going that way. That's really strange. That's one really weird thing you have to explain about the magnetic field is why does it do that? So, but going back to Maxwell's explanation, let's see here. So he's got this idea that there is this molecular vortex model. It says for a uniform magnetic field, the field lines pointed outward from the display screen, so they're pointed towards us. It can be observed from the black dots in the middle of the hexagons. The vortex of each hexagonal molecule rotates counterclockwise. The small green circles are clockwise rotating particles sandwiching between the molecular vortices.
Okay,
So,
Max, can I interject for a moment? What you got on screen, I think, comes from the paper that he had published in about 1861. Then it's a few years later, approximately 1864-65. That's the paper in which he created or developed the equations that have stood the test of time. In that second paper, he specifically walks away from the vortex approach that he took a few years earlier. So it's quite necessary, I think, not to apply what he said earlier in speculation, admittedly, about vortices to what he developed a few years later and that are the backbone to magnetism equations today. So just a word of warning there, Franklin. I think we're walking into a situation where one paper is specifically walked away from in the more important later paper, and we're looking at the earlier one at the moment in regard to vortices. Do you follow what I'm getting at?
I did hear about that. I'm not that familiar with this particular theory, but I did understand that Lee later did walk away from this. Mm-hmm. Although this might be interesting for us just because this is a particular physical example of how magnetic fields could be realized in a mechanical sense. So in this picture, these hexagons represent the magnetic fields coming towards us. So like in a standard magnet, you've got your North Pole, you've got your South Pole. They will show magnetic fields flowing from the north to the south. And we generally observe that, like if we stick iron filings on paper and we stick a magnet on that, we can see what look like lines. So this is saying that each of these lines is a spinning vortex, and in between each of these spinning vortexes is some other particle. that's kind of acting like, I guess, a wheel. I guess like the green little particles would be spinning basically in the opposite direction. Although if we try and apply what we know about how magnetic fields work, I really don't understand how this works, because basically an electron, if it were coming from, say, the left-hand side of the page here, and it enters this magnetic field, the force, let's see, the force would actually be deflected either up or down, right? So you've got, well, actually, let's see here. The force is coming in this way. The magnetic field is in the page. Yeah, so the force would actually be up. So that an electron coming into this structure would actually have to feel some kind of force it to go up or down, depending on which direction it came into. See, that's the other weird thing, is the force, as it enters the magnetic field line, it reverses itself depending on which direction it enters. So if it entered from the left, it would go down. If it entered from the right, it would go up. So, and I don't see how this picture helps with that. But I think it kind of helps us, at least imagine what kind of thing we're dealing with as far as magnetic field goes. So that's Maxwell's idea of that. Let me just bring up the hyperphysics. If you guys aren't familiar, this is hyperphysics is a good place to go that has general information on mainstream ideas. So here we have probably all the things that the mainstream thinks they knows about electricity and magnetism. So very interesting here. So let's see what they have to say about the magnetic field. So we click on magnetic field. We see the known things, which are that magnetic fields are produced by electric currents. Of course, I'd also say that magnetic fields are produced by permanent magnets. So what does that mean? Does anyone care to speculate on if magnetic fields are produced by electric currents, then what is going on with permanent magnets? Is there a relationship between those two? Would anyone like to speculate what that might mean? Or how that might work? What is the relationship between permanent magnetism and magnetism which is produced by electricity? Or should we consider those two things completely different? Go ahead.
I have some thoughts on that, but I don't have all the answers. I've always seen kind of the electric field as being the combined effects of the angular momentum of the particles, which I guess could be the ether, which kind of creates the field. And when you have the when it's formed by a permanent magnet, I think that the the combined angular momentum of the particles in the magnet are already naturally aligned, so they already have the combined angular momentum and create their own field. But in the when the electric current establishes the magnetic field, it's the electric current, that establishes the combined angular momentum, which then creates the electric or the magnetic field.
What do you mean by angular momentum? How does this relate to the magnetic field?
I don't have all the answers for that, but I really feel, I've always felt strongly that the magnetic field is created. I think of it like like millions of gyroscopes. It's just the combined angular momentum of possibly the ether or the particles within the field, that they're somehow aligned. Um, not necessarily all of them, but the majority of the particles are aligned in such a way where the angular momentum of them creates the field.
Yeah, but then the periphery of the gyroscope must be electrically charged. Then you get a kind of electric current that then creates the magnetic field.
Yeah, that's true.
Well, I think that's part. Well, this is what I hear so far as permanent magnetism goes. I mean, there's one theory that says that if there's some inherent magnetic field in an atom or something like that, and what you do is that if you point all of those magnetic things in the same direction, then that will create in that material an overall magnetic field from all of the smaller magnetic fields. Although I don't think they particularly say that there's a current loop in the magnet. I suppose that's one of the theories, is that, say, around the ferromagnetic atom, like iron, that if electrons are orbiting, that if they are all, that there must be some certain group of electrons which are orbiting as a current loop, and once you have anything going in a loop as an electron, then that generates whatever the magnetic field is. So if you then take all those atoms and align them in the same direction, all those little magnetic fields will add up into a big magnetic field. So in that way, the relationship would be that electric currents are still creating magnetic fields, but that would be done at the atomic level and at, say, the electron orbital level. And that, so it would, once again, just be like running current through a loop, except it'd be much smaller loops, is one possible interpretation of how that works. Although
the spin of elementary particles interacts with magnetic fields, so it can generate magnetic fields. It's that's how the magnetic resonance machines that are used in hospitals work. They interact with the spin of molecular groups in the body.
Yes, that's true. That we do have this concept of spin, which may or may not be different or similar to the concept of magnetic field. Although I have a hard time dealing with what spin is. All we really know about spin is that, as you say, it does interact with the magnetic field. If you send an atom with a particular spin through a magnetic field, it'll deflect one way or the other. And then that somehow they call that spin. Now, what you're proposing is something different, which is you're saying that not only does it interact with the magnetic field, but it actually causes the magnetic field, which may be possible. I mean, if it's not magnetic, how could it interact? Although we do know that like bare electrons, if you send them through a magnetic field, those also deflect. So, but does the electron itself bear the magnetic field by itself? If it did, then there's like an individual electron, like a magnet.
Yeah, but also neutral particles can have spin, and that spin also interacts with magnetic fields.
Well, perhaps that's another piece of evidence. I think what I'm trying to do here is that So we're truly trying to, I don't really know that anyone has the answer, but we'd like to work on it. We're going to find out what we can about the magnetic field and then speculate, even make up some new theories right here. So that's what I want you guys to put your thinking cap on. Let's see whether we can come up with some theory at the end of this that might explain the mysterious behavior of magnetism. So we have so far Maxwell's ideas about spin. I'm going to keep track of this in my notes here. Let's see. So my meeting notes, we have, let me share that.
I have treated the equivalent of the magnetic field in quaternionic differential calculus in the Hubble book model project, which is now on Wikiversity. And I have put the link to this stuff on the chat box.
So we're talking about Maxwell's vortices, and we're looking at hyperphysics, magnetism. So if you ever want to find anything about mainstream science, just go to hyperphysics. And they're investigating the first thing, which is magnetism caused by electric currents and the relationship between permanent magnets. Okay, so we have that. Now, getting back to hyperphysics, see what else we can find out about the magnetic field. So we find that the magnetic field is defined in terms of force on a moving charge in the Lorentz force law. Okay, that was the one I was looking for. The interaction of the magnetic field with charge leads to many practical applications. Magnetic field sources are essentially dipolar in nature, having a north and south pole. So here we have various things that have magnetic fields. So first of all, just running a current in a wire, that creates a magnetic field. So if you put a compass, just a single wire by a compass, and you turn on the current, you'll see the compass turn in response to that. So it doesn't take very much to make a magnetic field. Just the simplest magnet is just always made by running a current in a wire. Now, if we loop the wire, we also get a magnetic field. And this is where it clearly shows a north and a south. I think like when we have just run current in a wire, it's really hard to say, well, what's the north and what's the south pole of that thing? But when you start putting it in a loop, then we start getting a more obvious north and south pole. And if you put it in lots of loops, then we can clearly see the north pole sticking out of one end of the loop and the south pole sticking out of the other loop. And we also see a very similar thing with the bar magnet, which acts just like the solenoid, except it doesn't seem to have the apparent need of a coil of wire in it. And then we have the Earth, which also has a large magnetic field for some mysterious reason. And I also note that magnetic fields are not inherent to planetary bodies. It's like Mars has very, very little magnetic field relative to the Earth. Venus has very, very little magnetic field relative to the Earth. But something like, I believe, Saturn or Jupiter, they do have large magnetic fields. So it's not like all planetary objects have magnetic fields. But I just want to make a note between the solenoid and the bar magnet, that since that they both kind of look the same, it's almost like whatever's in the bar magnet must have the electric current going in the same kind of ways. So I would speculate that whatever's in the bar magnet, if it is a circulation of current, it would be just like the solenoid, because the physical orientation is the same. Perhaps it might be a whole bunch of small individual loops. If there are loops, they would be oriented in the same way as a solenoid, I would think, as a speculation. Okay, so here is, go ahead.
Someone point out that you can't really have an isolated current in a wire. There's, it's a current, so it's got to have a loop. It might be a very big loop, but there's still a current flows, has.
That's true, and there's no way you can have. I mean, it's got to be connected on both ends. So eventually, it probably does have to be a loop. So, and that way, I guess you could figure out what the north and south pole of that thing is. You'd have to follow it back to the battery. And eventually, one side of that would be north and the other side would be south. So that's true.
Yeah.
So let's see here. So we have the Lorentz force law. So the total force is a result of the electric force. So the E would have been any electrostatic field present. Because if you take a electron and you shoot it between a positively charged plate and a negatively charged plate, you will see that the electron will, of course, be attracted to the positive plate and repelled by the negative plate, and it will deflect down towards the positive. And I think we understand how that works, at least, that's just an attraction of opposite charges. But now the magnetic field is a completely different animal, where you have the charge and its velocity cross the cross product of the magnetic field. So such that they have this picture here with the north and the south pole, and the magnetic field line, which is represented by B, is pointing downward between the north and south. So the field line is right between those two magnets. And if you shoot an electron from the left to the right, the electron will actually be heading at us, towards us, or away from us. So that's really, really weird. That like the field line is pointing down, the velocity of the electron is left to right, but the electron will be deflected towards us or away from us. This is a little bit like if you have a fan and it's blowing outward towards you, and you put up some paper into the fan, you think that the paper would flow with the air, but instead of doing that, it like blows to the right, you know. So that's what's really weird about that. So the magnetic field line is the Tesla. And let's look at the right-hand rule here. I think this kind of describes, this picture here describes, the nature of the force as coming at a completely different angle than either the direction of the electron or the direction of the magnetic field. Let's see what else we can find out about magnetism on this. We have Ampere's line, Ampere's law. We have Biot-Savart law, which is, what is this? Which I guess is describing the magnetic density. Now we also have something on magnetic domains. Okay, so this is an explanation here about what's going on with permanent magnets. So permanent magnets have these little tiny domains, and they are generally randomly oriented. But when they apply an external field, they all become aligned. And that's what causes the materials to become magnetic. I think what's curious is, how do they make these super magnets? How do they make the best magnets? And one thing is that the magnetic material is actually non-conductive. And what they do is that they take it, they form it into something, a solid, and then they basically sand it off into the smallest particles possible, right? So you turn this thing, you make this material, then you turn it into dust. And then what you do is that you stick that in the shape of the magnet that you want. Then you apply a strong magnetic field to it while they're still loose. And what I believe that does is that since you turn this material into dust, they can still move around like individual little magnets. And then when you stick it in a strong magnetic field, that causes all the natural domains to align with that magnetic field. And then what they do is they sinter that whole thing together. Sintering meaning that you basically press it together with extreme force and heat to cause all the elements to bond to each other. So you're not melting it or anything, you're sintering it to keep that orientation. But in that case, it's like you're just making a billion little teeny magnets, aligning them all together and then gluing it together. Is how they make these magnets. But it's interesting that they have to make it that way, that they start with small but still macroscopic particles, and they join those all together to make a magnet. Now we also have a property in the magnetic field called permeability. Let's see, what's permeability? Permeability is what? I believe it's the degree to which something can be magnetized. Let's see, table of magnetic properties. So this is apparently the degree at which it can hold a magnetic field. There's two main properties of space, is permittivity and permeability. I think permeability has to do with the ability, magnetic constant, permeability of space. I'm not getting a real good definition of what the permeability of space is, or what permeability is, but it is a important aspect of magnetism. Then we have Faraday's law. And this is a relationship between magnetic fields and voltages that are induced in a coil. So whenever we have varying magnetic fields, somehow generates electric currents. So not only do electric currents generate magnetic fields, but varying magnetic fields generate currents. So that is another interesting clue as to what's going on here. Now, I did do an experiment because I was explaining that the magnetic field is generated purely by electric current. And it's like my brother, he didn't believe me at all because, you know, every single solenoid we know about, it's like in order to generate electromagnet, you got to wrap a wire around a nail and things like that. But I wanted to show him that you don't need to do that, that you can just take a bare loop of wire and you can put electric current through it. And that alone, without the presence of any ferromagnetic materials at all, you know, just copper wire, insulated copper wire, will display the magnetic field attraction. So that's all you need to do that. So let me see if I can bring up perhaps some of my YouTube videos on that. I do have a few videos on the magnetic field that might be of interest here. So let me see if I can go find that. Just a moment here. Let's see, I'm getting a little bit of noise out here from people. So if you're not speaking, please mute your line so we don't hear. It sounds like there's some dishes clanking in the background. I can't tell who that is. Okay, I think that might have been Jim there. Okay, so let me go look and see whether I can find some interesting videos on the magnetic field for you. And there are some people on YouTube who also have some idea of how the magnetic field works. So maybe we'll take a look at some of those videos. One of them has to do with relativity, and that somehow the relative speed of the electron somehow causes an attraction. I think that's really, really weird idea. Okay, so I have my channel here, and I've got all kinds of videos. Let's see if I can find my magnetic field videos here. Those would be my earlier videos here. As you can see, I've been busy on YouTube here. I think we're getting close. It's one of these here. Let's just search for magnets here. No, that's not right. Now we search on just my videos. Oh, here we go. Here's a here's my video just showing a plain loop of wire on a magnet here. So all we have here is that as I've got a yellow magnet here, that's a permanent magnet, and then we have a loop of wire here. So all I'm doing is applying a electric field to this thing. Let me see if I can let you listen here. The yellow thing you see back there is a magnet, and I hook this up to 3 volts batteries, and it's set up to this key. So when I depress this key, current is going to flow through these wires, and it's going to loop around the wire and then come out the other end. And what I contend is that the electrons will deflect towards the magnet, just like they would say in a TV set, but because the electrons are trapped within the wire and they can't escape the wire, they drag the whole loop of wire towards the magnet. So let's see what happens when I depress the key. There you go. Bare loop of wire. I depress the key, it becomes attracted to the magnet. And before I do that, there's no attraction. Only when I depress the key is there an attraction. And so there you go. That's a direct demonstration of a simple loop of wire being attracted to a magnet. Okay, so were you guys able to hear that? You guys able to hear that explanation?
I hardly understood it. I didn't hear very much.
Yeah, it's a little bit hard. So there I'm speculating on what causes the magnetic attraction in one way. So if we know that we can deflect an electron in a magnetic field, so that is how like old CRTs used to work, right? So, and the direction of the deflection is consistent with what we see with the magnetic field law. So if electrons deflect in a magnetic field, right, then suppose that instead of having a CRT with an electron beam spraying an electron beam towards a screen, instead we put those electrons in a wire, right? So instead of a electron beam, we stick those in a wire, and then we put it in the same magnetic field that would cause it to deflect down. What would happen to that wire? What would you think would happen to the electrons if I just stuck them in a wire and then placed them in the same magnetic field that would have normally caused the electrons to deflect downward? What do you think would happen to that physical wire? Anybody bother to speculate? Would it feel no force? Would it? What would you think would happen?
I would guess it would be deflected down also.
Yeah, that's what I would think. That if you stuck a wire in the same physical situation as the electron beam that would have been deflected downward, that the electrons inside the wire would also feel that downward deflection, but the electrons can't escape the wire. They're stuck in the bounds of the wire. So the electrons would physically be trying to push down. They would actually end up pushing down on the atoms of the metal. I mean, first they would go from the top of the wire down to the bottom of the wire, and then when they hit the bottom of the wire, they would hit the insulator that couldn't get any further, and so the only force they can exert is actually be on the wire itself.
Yeah, I don't think.
My understanding is that the electrons are a gas inside the wire. So you're telling me that a gas exerts a force on the wire?
Yeah,
Yes, that's would be my assertion.
I don't see how a gas exerts a force on a solid.
There has to be a current in the wire.
Yes, there has to be, because first I started with the example of you have an electron beam in a CRT, and those magnets are set such that it would cause the electron beam to deflect downward, right? So those electrons are feeling a magnetic force causing them to go down, right? Because otherwise, if you turn off the magnetic field, those electrons would just go straight and hit the middle of the screen. But you turn on the magnetic field, those deflect downward, right? So they are feeling a force.
The electrons have
feeling a force.
velocities, they're a current.
Yes, they have a current.
They
need a current.
They are a current.
Because if they are a current, yes. The beam that comes out of the back of the CRT and hits the front of the screen is in fact a current.
And that's generating a magnetic field. It interacts with the magnetic field of the coils around the CRT.
Seems to me you're confusing two different things. You're telling me that a CRT that's shooting electrons out, which are basically, we don't even know really what they are or what they look like. They're just sort of a speculative entity. And presumably they're tiny little gas-like particles that go shooting out in a stream. So what you have is a stream of gas, basically. All right. And now you're trying to tell me that that gas, that this bunch of particles, which we can't really define, is exerting a force inside the wire. I don't really see how that works. Sorry.
Well, it would have to be a current in the wire. If the electrons are moving in random directions, there's no net force.
Well, basically, according to what Franklin's saying electrons and current are the same thing. So now you have this identification that seems kind of, where's your proof?
Well, the mainstream saying is it's the movement of the electrons, not the and perhaps some weak spin function.
Well, we know what the force law is, which is V cross B. So we know that that describes a force on electrons. So I think it's fair to
know what it is. So you're saying we know this force on this mysterious entity called electrons, which we're not really exactly sure what that is, right?
Yes, but we're pretty sure that. I mean, some people question whether current is a flow.
You're the one that's making the assertions.
Yes, I'm making some assertions. I mean, we're just speculating here about what is the basics of magnetic force. So I think people would say that they clearly understand what's going on in a CRT. Where you've got a magnetic field, you've got an electron beam. That beam bends in the magnetic fields.
Why is that your starting point? I mean, historically, that's not the starting point at all. The starting point is Ampere's experiments that were performed in the 1820s. That's the fundamental starting point of the whole theory is Ampere's experiments. And he showed that when you, quote, put a current, which they thought a current was some kind of electricity. They thought electricity was some kind of material entity that flowed through the wires from the positive terminal to the negative terminal of the battery or the source. And he showed that there was a force exerted between the wires. Okay, that's basically the starting point of electromagnetic theory. You're talking about a CRT. That's not the starting point of electromagnetic theory.
That is correct. But let's see, we're talking about which law is that? That's going back to the magnetic field here, the Lorentz force law. So Lorentz establishes his force law. Now the question is that now we're just speculating here. So I just showed you a demonstration of a coil of wire being used to interact with a permanent magnet. Now, actually, you don't actually need a coil of wire. If I had just even a straight piece of wire and I energized it, you would see it actually being attracted or repelled from the magnet just as a straight piece of wire. So the question is, how is that happening? And so I start with the CRT because it's an example that I think people are familiar with.
But historically, this doesn't mean anything. This is the origin of electromagnetic theory is Coulomb's law. This isn't Coulomb's law. Okay, this isn't Coulomb's law.
This is the Lorentz force law.
So you're starting completely from the wrong point. Okay, you have no idea what the historical progress of electromagnetic theory. Okay, you're just bringing up stuff, Lorentz force law, which didn't come into electromagnetic theory towards the end of the 19th century. Okay, well, people knew all about magnetism and Faraday's law and all these other things long before this Lorentz force law ever came into existence. So I don't see why your argument is being based on something that didn't come into existence until the end of the 19th century.
Well, I don't think we're trying to come up with a history lesson here. We're trying to come up with explaining
I would say I'd say your argument isn't really based on a logical progression of experimental evidence. The logical progression starts in Coulomb's law and in the 18th century, not at the end of the 19th century. So I think this is all mixed up.
Well, what do other people think? I mean, the presumption that is being put forth here is that an electron beam bends in a magnetic field. So if we just put the magnetic beam in a piece of wire, that will also cause the wire to bend down. That is the supposition.
Can you hear me? Can you hear me?
Yes, we can hear you.
Okay, I think that Harry is absolutely wrong in this argumentation, because we must start from that point that these people, Ampere and so in old times, they didn't knew the basic things which are new after the 19, for instance, 11. They didn't knew what and what amount, what they are doing with. We knew after millican that electron, what is electron, what amount of charge it has. So in fact, if you will start with as proposed here, the Harry, it's absolutely nonsense, because from these experiments which they do,
you can. Wait a minute. You just said that the fundamental basis of electromagnetic theory is nonsense.
I didn't interrupt.
The fundamental basis of electromagnetic theory is nonsense.
I didn't interrupt you, so please do
yes, you did. You just said it's nonsense, and you said I was absolutely wrong, and you provided nothing to back it up.
Some things about this. So if I'm starting, I am asked if I can talk. So Harry, please don't interrupt me. And if you will start to talk, I will not interrupt you. So
please don't declare me wrong.
With my
please don't declare me wrong.
Because
please don't declare something wrong.
All right, people, let's all just talk at once. Otherwise, I will have to mute one of you. Okay?
Of course. So so you have to do this.
But Peter, please.
Who will raise the flag? That one will speak. But Harry has some privileges as he speaks whenever he wants, and if anybody other starts to speak, so he immediately interrupts him as well. Who is here? So let he do himself. So I say again that these old physicists in all they do not knew what we knew today. So Franklin, in fact, is right, because we have to start, in fact, after millican, so after 1911, because it was the point that we came to that, where we can really focus on what is inside. They don't know what is in there. We knew at least how many how many atoms of charge are there in this wire, which you show here and so. So that's my opinion about this. Thank you.
Okay. All right. You said your piece. I want to know how this force on this cloud or gas of electrons inside this wire exerts the force on the wire.
There is no gas of electron inside that wire.
All right. So that's what so what is there? What's going on inside that wire?
You have start from the first point. How this gas or how this current start to exist there. It start to exist there. The first point is that you must put on both sides of this wire a force. This is the starting point of all. Not that there is now the current. You must put a force there. That is the absolutely basic, but also the Franklin is down. If we switch the button at that point, the force with velocity of light is going through this wire, and all other is subsequential effects. So if you start to think about these experiments which Franklin is showing here, very nice. So you must start from the point that when you switch the button. So when you install the first force in this coil, that if you switch the button in that moment with velocity of light, the force is going in this, and all other effects are the side effect of this. So what is happened there? You switch the bottom, and the electric force, so I mean ether, the force of ether, electric force, pressure ether is going through this coil, and then the side effect is in fact the magnetic force is the side effect of this. That is the pressure which press the electron, and on the side effect is magnetic and electric. There is also the electric force which is caused there, but it is in line in this coil, and you don't see it, but it is there. And this, so
okay, so you're telling me there's this thing called an electric force that's there because you say so.
You must speak slowly. I am not born Englishman, and your
Well,
English.
you just said that there's something called an electric force that makes everything happen, but you never. I don't know where this force came from. Where did this force come from?
It is another question, but we are not discussing now this.
Where did it come from?
We are starting in the point that we have a force, that force there.
Oh, so you just assume it exists.
Well, I think we're starting from the fact that the Lorentz force law is valid. Now, now Harry is asking the deeper question of why does this happen? But I think that
question at all. I'm not asking that question at all. You're using something called B and something called E and another thing called Q, okay, and this other thing called F. And you're saying that these thing that B, that we don't know what B is, and another thing called E, we don't know what that is. And then we have another thing called F, and we don't know what that is either. And we don't even know what Q is. And you're trying to tell me, you know, that you're going to explain everything based on a lot of this unknown stuff that you're talking about that you think exists?
Yes, actually, because all of these things are known. We do know what the Q is.
Yeah,
we know what the B is. We know what the B is. This is all very well known.
They're known because of what happened to electromagnetic theory earlier than when this Lorentz force law came into existence. And you're saying, oh no, we can ignore everything that happened before the end of the 19th century. No, you can't do
that. Yes, it happened.
I don't believe I've done any such thing.
Yeah, you couldn't explain on all these experiments which was done before, nothing from this, because you must start with exactly with the beginning of the 19th century. I think that, for instance, I think that heavy side was very far, but I think the more far scientists who is the Mir, which is, I don't know if it is known to you or not, but it is very deeply pressed under the ground, because he was, in fact, I think he was the scientist who was at the top level of thinking about all these things, but he was very, very strictly against Einstein, and he criticized them, and today science don't want the field, don't know the electric field, magnetic field, gravity field. They have time space. So, but if anybody really want to start somewhere, so I think that I don't know if you know the Mir works, but it was very, very important scientist in around 1911, 1905, I think in Germany, and they work, and he really connect this electricity and magneticity with ether, which is around it, and with basic states of ether. I think it is very interesting reading. Thank you.
Yeah, let's just try and stick with, I mean, I don't want to get into history and stuff. I think like this little experiment that I did here with the magnet and the loop
Okay,
of
but
coil
what's
wire.
this B thing?
Anyone
And
can
go back
start
to
with
this
that.
equation. Go back to this equation. What is B?
B is the direction of the magnetic field. So between
Now,
the
what's
north
the
and the
magnetic
south pole,
field? What's the magnetic field?
the
Where does it
magnetic
say,
field
where
is
does it
the
say
thing
B
that
is magnetic field?
right
Where does
there,
it
right
say
there
B
and
is
there.
magnetic field? Okay.
B is magnetic
B is
field right there.
magnetic
So
field.
it's magnetic field B.
So what is H?
I mean, you're really not familiar with these terms. These are very common terms. B is the
Well,
magnetic field vector.
H is the magnetic field, not B.
Well, in this nomenclature, it's B. I have seen it as H though. So that's another
Okay, so now you're
confusing
telling me, now you define a magnetic field as B, where in other books, they define the magnetic field as H. So why are you
Yes, that's
using
true.
this definition here? Explain that to me.
Because this comes from hyperphysics, and it just happens to be a handy source. But I don't want to be I don't want to be debating nomenclature. I think one thing that gets really annoying in discussions is like getting into like what do you call things?
You have to address that. You know, you just can't say, oh, the nomenclature is unimportant. That's the most important thing.
No, I would disagree. I mean, this is like if you were
Well,
having a
how do you know
story.
what you're talking about? You know, there's all these different ways of writing down Maxwell's equations. You know how many different ways there are to write down Maxwell's
That's
equations?
why
Why
during
did
these
you
discussions,
pick this particular one?
it's handy.
Why did you pick this particular
But
one?
once again, I don't want to get into what difference in nomenclature is that if you realize there's a difference in nomenclature, you just say, oh, there's a difference. Okay, good. I now understand that B is the same as H. And that's all you should have to do. I don't want to spend 5 minutes explaining why I picked this website. That would be a useless waste of our time. But now that you understand what those things are,
so in other words, it's arbitrary.
it is totally arbitrary. I could call it Mickey Mouse. And as long as you understood what it was, then it's fine.
Your whole argument is basically arbitrary.
No, it's not. This equation, Lorentz force law, is true. What nomenclature you use to describe each component of it is a matter of convention. Okay.
Now, but your argument is, what exactly is your argument? Okay, what is your argument? What's
my argument is I'm trying to figure out what is the basis of the magnetic force that we observe in this simple experiment with the loop of wire and the magnet. Now, the very basic.
So your claim is, now let me understand. Your claim is that the force is exerted on the electrons inside the wire.
Franklin, yeah, I really must to step inside.
Let him speak. Let Harry
Franklin,
speak.
you are the leader
of
the conference, and you really have to switch the people who are there and put the world, the peoples one after another, because this Harry absolutely understand what this discussion is about. We all knew that Franklin is not the top specialist. We all knew that Franklin is the mediator who puts Who puts the
Can you please
pressure
let
here?
Harry speak?
I want to know how the force on
Seems
these
to me that Harry
electrons
wants to this,
that are
Harry
moving
wants
through the wire causes the wire to move.
brush away this discussion and to bring away all these NPA sessions. So Franklin, you really have to power, and you really have to do it that way that you must switch everybody, and who will raise the flag, you will give him the word, because in this case Harry will break all this discussion, and you see how it is going on.
No, Peter.
Starts to
Peter,
talk.
can you stop?
Okay,
Stop.
you must
Stop.
give an order. Okay.
Stop, Peter. Because, you know, Harry was saying something very important about trying to understand what I was saying. And I want to let him see whether he understands that particular speculation. All right. So Harry, go ahead. So from what I understand, so you understand what I was speculating, which is that the force on the wire that we observe is actually being created by the electrons being deflected towards the magnet. And that is the basic speculation here. Now, your
Okay,
second
but
question is that you want to know.
Here's my point. My point is, how does this force that's exerted on the quote electrons, and you don't know what these electrons are, you don't know how they're moving through the wire, okay, how does this force on electrons that presumably are floating around in this wire, how does that cause the wire to move?
But another question is not needed. The question is here from Franklin and Harry, or say your opinion or don't bring another question. It's stupid. How you
Well,
take
Harry, let me ask you this question.
opinion to Franklin, or don't, you are asking from Franklin, that we all knew that Franklin is not top specialist, almost not top specialist in all of these fields what we want to discuss here. So that I think that the sense of this is that Franklin is raising questions, and our task is to try to make an answer to these questions and think the answer of
Well, let me ask Harry a question. Can I ask Harry a question? Okay, Harry. Suppose that the electrons are, like you say, a gas in the wire. They actually represent physical particles, you know, like a bit of sand or something is a particle. So we have this gas, it's in the wire.
I don't subscribe to, first off, you have to tell me what these particles are. You're making the assertion. Since I don't know.
Yes, I'm making the assertion.
I'm just basically going on, I don't know what particular theory you're operating on. You know, you have the band theory, and then there's the Drude theory, which is that it's a gas of kind of like a.
Well, your question is. Well, your question is, what causes the electrons to exert a force on the wire? That is your question. Is that correct?
I want to know why the electrons just don't crowd on to the side of the wire, or why the electrons don't squirt backwards out of the wire. What makes you think? I mean, I don't see how this force that you're talking about causes the wire to move. How does that happen?
Well, do you agree that there's forces on the electrons? As the electrons move through the wire,
that's your fundamental, that's your assumption. I don't necessarily agree to it, but that's your assumption that you're starting from.
Yes, that's my assumption, that due to the law, Lorenz's law, that as the electrons move through the wire, they must feel a force is in fact exerted on those electrons as they move through the magnetic field. And let's say there's a force moving that causes the electrons to go this way, okay, regardless of whatever. Now, your question is that if we have an electron and it's in a wire, let's say this is CD is like the wire, right? Okay, so there's some force due to the Lorentz or the Lorenz's law that's causing the electron to be deflected this way. Now, what's happening is, okay, what's going to happen to the electron when it hits the end of the wire. Now it can't go any further. So what's it going to do? What do you think, Harry? What is going to happen to the force of this electron trying to go this way, but it can't because it meets the insulator? What's going to happen to that force?
Well, that's your responsibility to answer because you're the guy who's making the assertion, not me.
Well, what do other people think? What's going to happen to that force?
You have to distinguish between two situations. As I understand it, we are now talking about not about the permanent current, yes, not the alternative. We are talking about permanent, so current, not alternative current, yes. So we are not talking what will be do if you put this your coil in the socket where the so if you have a DC current, so the electrons will eliminate the force on both sides of batteries. Then you need to have the batteries. Batteries are polarized two places where the difference potential is, yes? So when the electrons come to the end of the wire, and if you have connected to battery, you are asking about this? Or is this the answer to your question?
I don't think so. I mean, Peter, what do you think if I have this is a wire. I mean, this is, sticking towards the screen here. And then I have an electron which is being deflected in the magnetic field this direction. What is going to happen to the physical wire? Because
you don't mean the electron inside the wire, but outside the wire, mean?
No, inside the wire. Inside the wire is an electron which is being deflected. Now the electron is actually moving this way towards the screen, but it's being deflected.
Maybe on
surface. Going that way.
Maybe they are moving on surface. Maybe they are not a particle, but they are just vortices which are moving very slowly.
No, I think you're thinking too complicated, right? All I'm talking about is that it's like if I have this sticker.
For sure, they are not electrons, they are a particle. It's clear, yes. You can't.
If I put the question, I think the question I'm asking is pretty simple, but I'm not going to give you the answer because I think you really have to answer it yourself. But you're not
like a known amount of charge. So this charge is traveling. So this charge is somehow traveling through the wire.
Just a second, I think.
To the wire and to the battery, and this charge will flow into the battery.
Yes, we know that. But that just creates a flow of electrons. So if I have, let's say I have this sticker here, and the sticker is stuck to the CD. And if I pull the sticker to the left, what's going to happen to the CD? Is it going to stay in place?
You don't have any idea about what the electron is to begin with. Then you don't have an idea what current is really. What is current? What's going on inside that wire? What is it?
A current is a flow of electrons. And this is why I brought up the CRT example as being a physical flow of particles.
Well, are the electrons like some kind of a water or a gas that goes flowing through the wire?
Yes, exactly. It's like particles, like water molecules.
Your claim is that electrons is like a flow of some kind of a gas or water that goes through the wire.
This is correct.
Okay.
I think most of the mainstream would agree with that.
May I make a remark? You're running into confusion with your Lorentz formula. The Lorentz law is showing an F, and that F stands for something. If something is moving, and it's accelerating, then this F means the formula F is m, the mass, times the acceleration. On the other side of the equation, there stands something with an electric charge. That is the Q in your equation. That stands for a particle. That particle is accelerated.
Yes, the particle is
So
accelerated.
you must interpret the left side of the equation. The left side of the equation is standing for movement of something. Movement maybe of the electron. It can be a proton. It can be anything that is charged with the charge with the value of Q. And it's operating in a field. And a field that's consisting of an electric field and a magnetic field. It's a combined field.
So Hans, so let's say we've got an electron, it's feeling a force.
Yeah.
And so that would cause the electron to say deflect towards the right, just arbitrarily.
If you say deflect, then it's already moving. Or
yes, it's absolutely moving.
Yeah. And
it's
so
absolutely moving, but it deflects towards the right.
That's the left side of the equation, which is not filled in.
Now let's suppose you put
something like F is m, the mass times the acceleration.
Now let's say we've got this electron, it's being deflected towards the right, but you put something in its way so that it can no longer, you put like some kind of wall. Yeah. And so
it can no longer move. So your V becomes 0.
No, not the V. The V is still going in the direction of the current. There's no difference in the V.
Good. Yeah, then
there's no difference in the V.
The sidewall and the electron is moving some impulse on some momentum onto each other.
It's like you've got, let's say you've got a pipe and it's got some water in it, right?
Yeah. The water molecules have a momentum on the sidewall of the pipe, so they cannot go out. And that's the same with the electrons in the wire. The electrons cannot leave the wire.
Well, see, I'm not sure. Let's say let's put up a real. Let's say we've got water and we put magnetic iron filings in the water, right?
Yeah.
And then what we do is that we put a magnet, a very strong magnet, next to this flowing water.
Yeah.
And which causes the magnetic little bits to be attracted to the magnet, right?
If the water molecules were charged, you would have a kind of current in
wait a minute, wait, please. I'm just trying to come up with some analogy because I'm trying to get someone to say, which is, well, actually I think Harry already said it, which was that the electrons are being attracted to the magnet. And because the electrons are being attracted to the magnet, when they run into the barrier of the wire, they push the wire physically towards the magnet, since the charges themselves cannot.
But then they would have to stop, Franklin, to do the pushing. They would have to stop, in which case the force would disappear, which was what Hans was explaining to you.
No, this thing is that the force.
Once they do the pushing, in order for the electrons to stop, to push the wire,
they do not stop.
They lose the force that's exerted on them, and so the force disappears. So you have no force.
No.
So the force is
the force. This is the cross product. Remember, the force is exerted at right angles to the direction of the electron flow.
In order for that to happen, the electrons have to stop.
No, they don't. The force is do you understand it? The force is exerted at 90 degrees to the direction of the current.
What I don't understand is how the electrons are pushing at 90 degrees and still be moving.
Again, the equation must be read carefully, because the cross product means that only the component of the velocity that's perpendicular to the magnetic field is having influence. The other component that's perpendicular to it that's in the for example in the direction of the sidewall of the wire has no influence.
Well, let me answer Harry's question. Harry's question is very important. So I have just a single straight wire. Okay, Harry, I've got an electric current flowing through that wire. The velocity is between the, like, let's say it's coming out of the page, right? So the velocity is coming out of the page. So that's the velocity of the electrons. That never changes. But the force that's exerted is at 90 degrees to that flow. So that would be towards the right. So the force is being exerted towards the right. The current is flowing into the page. So when the velocity that we're talking about is not the velocity that's in the direction of the force. So when the electron goes and it is deflected towards the right, I mean, it's flowing down the wire the whole time, but it goes from the left-hand side of the wire to the right-hand side of the wire. Now the velocity relative to where the force is zero, but the only velocity that matters is the 90-degree force, which is still flowing into the page. So yes, the velocity of the electron hasn't changed at all. It's just being it's just feeling a force still towards the right. It's just flowing down the wire the whole time while it's sitting on the right-hand side of the wire. That's why I was trying to bring up, you know, what would happen if you
as
had,
far
like,
as I can say,
some
the only
particle.
thing you can convince me of is that all of the electrons would crowd onto one side of the wire, but I don't see any reason why they would exert a force on the wire that would cause it to move. Sorry.
Well, if they were free, then they would continue towards the right, right? There's a force being exerted on those electrons.
Yeah,
but it's the force exerted
right?
on the
There's a
wire
force being
that you're
exerted.
trying to account for, not the force on the electrons. What the experiment shows is
Yes,
that
but the
there's a force
electron
on the wire, not a force on the electrons.
Yes,
The electrons is an hypothesis on your part.
yes. Well, the electron, I'm trying to explain that. So the electron is a particle within the wire. It's a physical particle.
So all you have, in
So
my
when
opinion, is that you've caused the electrons to crowd to one side of the wire, but that doesn't tell me that there's going to be a force on the wire that will cause it
well,
to
there's
move.
still going to be a force on those electrons, even as they're crowded to the right. Now, if I have, like, it's like if I have a bunch of birds in a cage, I suppose, and if they all flew towards the right, you know,
The
what's
cage
going to
is
happen?
gonna move?
Is the cage going to move if all the birds are
I
flying
don't
towards
think
the right?
so.
Is the cage going to move towards the right?
Well, my explanation of your experiment is that the so-called current in the wire makes the coil into a magnet, and it is the magnetic force between the permanent magnet and the induced magnet of the coil that causes the coil to move.
No, that's not at all what I'm trying to say. I mean,
Well, I
that's the
know
very, very
that's why
generic
I'm saying that you're wrong,
explanation.
because I'm saying that you're wrong because it's not the force on the electrons, it's the magnetic force between the coil and the magnet that causes the coil to move.
Yeah, and I'm saying that's not an explanation.
Well, prove it.
Because you didn't explain what the magnetic force is. Well, you didn't explain what's actually compelling the wire to move towards the magnet.
the force.
So I'm just putting forth one speculation.
The force is only acting on the Q things, and the E and the B are fields. This is an interaction between the Q and the E and the B. The Q on the one side and the E and the B on the other side.
Well, let's see what other people think. I mean, Harry doesn't believe that if I have electrons and they're feeling a force towards the right, once they hit the end of the wire, they're not going to push the wire in the direction of the force. That's my speculation. So I wanted to hear from some other people, like Bill. Maybe perhaps Bill is that a reasonable speculation that if you have electrons, I mean, we haven't even talked about, what the magnetic field is, but if we believe that the Lorentz force law is correct, and we believe that electrons are flowing through the wire just like an electron beam, and if they're being deflected towards the right, that what we see in that experiment that I showed is all those electrons being deflected towards the permanent magnet, and then we see the entire wire being dragged along with it. Now, if we could determine that is the case, I think that would be very significant in understanding what is the physically observed. We observe the wire coil actually moving towards the magnet. And currently, we actually have zero idea in the mainstream exactly why that happening. So the speculation here is that it's actually the electrons that are being deflected towards the magnet, and that it's just dragging the whole wire with it. So what do you think, Bill? Is that reasonable speculation? I mean, I think that follows all of the laws of electrodynamics, doesn't it?
Well, most of the electrons in the atom will stay attached to the atom. So the force will be on the material. A few electrons will move, but the other thing is, Lorentz force law has been invalidated experimentally because magnetic monopoles have been found in many cases. In fact, I'm publishing an article in May in the Common Sense Science newsletter where I show how to make a magnetic monopole. And how to make them with bar magnets, with horseshoe magnets, and with disc magnets. And I show you how to measure with a compass that they are, or a series of compasses that they are magnetic monopoles. And monopoles are not taken into account by Lorentz's force law, and nor are they taken into account by Gauss's law for magnetostatics, where it says del dot B equals 0, because del dot B equals something. And that means that the solution to Maxwell's vector equations, as put forth by Oliver Heaviside, are no longer valid because there cannot be a vector potential A or a scalar potential psi as a solution to Maxwell's equations. Also, Maxwell did not take into account the 6 empirical equations of electrodynamics, so he has an incomplete version. And if you look at Maxwell's equations, they don't have any acceleration terms or dAdt, derivative acceleration terms, which means they don't describe the emission and absorption of radiation, and they don't describe the recoil.
Let's not get too far afield.
The Lorentz's force law doesn't have that in it. It doesn't have the.
Let's not discuss, the inaccuracies of the Lorentz force law.
Okay, it's known to be false. That's what I want to say. We're arguing
speculation
that have already been proven wrong experimentally. So why do we do that? Why don't
Bill, let me ask you this question. What do you have to comment about? Isn't the Lorentz force law doesn't obey Newton's third law of action and reaction? Do you agree with that?
Yes, Weber's version of electrodynamics does, and that came before Lorentz and his work. But he doesn't obey Newton's third law.
Well, but you haven't really answered.
Did you hear that? The Lorentz force law doesn't obey Newton's third law. So there's a contradiction there.
Well, what we do know, I mean, even if we didn't have any of these laws, is that we can observe deflections of electrons in magnetic fields. And that observation doesn't take you to believe any law at all. That's just an empirical observation. So, Bill, the question is about, do you think the speculation is reasonable that the reason why we are seeing the loop in my little experiment deflect towards the magnet is because it is the electrons in the wire that are being deflected towards the magnet?
Well, I guess the question is, what is an electron, and how do the electrons get free from the atoms to move? And most of them will not move. The inner electrons will not move. and but they are attached to the atoms, and they will move the bulk of the material that they're in. So that's what you're seeing, I think, when you do your.
Well, that's the significant explanation that I'm trying to at least come up with. That there are electrons, there are free electrons in conductors. You know, in a piece of plastic, there aren't really any free electrons, but in copper, certainly there are free electrons, which are being driven by the voltage source, like a battery, and that as they are deflected towards the magnetic field generated by that permanent magnet, that they cause the bulk of the wire to move in the same direction as the wire. Now, as simple a concept as that may seem, that would be, if that were true, that would be a much better explanation for the physical force that we feel. So let's see, who started out the beginning of the conference? Is he still here? They, wanted to know what possible explanations there could be. So I was wondering, does that get any closer to what we're looking for? I see Jim is here. Maybe Jim, maybe you want to comment. Would that be any kind of progress to explain, like when I have two magnets, what's causing those two things to come together, to explain that it's actually the electrons inside the magnets which are being exposed to the Lorentz force law, and they're just all we're seeing as a result of the Lorentz force law.
Well, that's certainly the mainstream position. I'm not sure I understand magnetism very well myself. Although,
well, have we made any progress towards trying to figure out what that magnetism is?
Well, on one hand, Franklin, here's the problem. You basically, your argument only addresses what happens in the loop of wire. You don't address what happens in the magnet. So you've left that out. So what is happening in the magnet? Are you gonna claim that the electrons in the magnet are held in place somehow, but you don't really even know how the magnetic field is being created in the first place in the magnet? So,
we can speculate on that, but
I think the whole
but for
thing
the moment, we're just concentrating on the fact that the permanent magnet is generating a magnetic field, and for the moment, we don't know how that's doing that.
Why can't you make the same assumption for the loop of wire? Why do you have to bring in this hypothesis of electrons?
Because we need something to actually exert the force on the wire. If
So
we didn't have the electrons,
exert a force on the wire, but we got nothing inside the magnet to exert the force.
No, it's just that we haven't explained that part of it yet. And actually, we only have 15 minutes left in the conference, so I don't think we're going to get around to explaining how the magnetic field comes out of the magnet.
I think you ought to start with the magnet first. That seems to be the bigger problem.
Well, we did start with the magnet, and that we explained that magnetic fields appear to be the result of electrical looped currents. Maybe you have a looped electrical current, we have magnetic field.
Yeah, I'd also like to point out that I think the Lorentz force law, you can derive the Biot-Savart law from that. And that's really a generalization of the Ampere law. So we're not really, another point, there's this book by Peter Beckman called Einstein Plus Two, where he essentially asserts that the Lorentz force law can be shown to, the B in the Lorentz force law can actually be shown to be the result of a moving E, a changing electric field. So that there is, essentially saying that there is no really unique field, B field, that is really a kind of an E field.
Let's see here. I think, Mitch, you started out with a question. I was wondering, what do you think of the conversation so far?
I think it's probably as good as an explanation of anything else, given the conventional thought of current flow, which I'm not sure if I believe the conventional thought either of what current flow is. But you did touch on something earlier I had a question on, and that's about the planets. Not all planets have a magnetic field. And I do have a question about that. You said that Mars and Venus really have very little. Are those two planets known to have iron core, molten iron cores?
I don't know, and I don't think it particularly matters. What seems to matter most is that the planet has an atmosphere, and it rotates relatively quickly.
Ah,
So Earth has a thick atmosphere and rotates relatively quickly. Therefore, it has a magnetic field. But say Venus has a very thick atmosphere, but it rotates hardly anything. And so that breaks the rule.
okay.
But you have like Saturn, which rotates both very quickly and has a very thick magnetic field. I mean, very thick atmosphere that has a magnetic field. And you have Mars, which rotates almost as fast as Earth, but has almost no atmosphere, and therefore it has very weak magnetic field. So it would seem to be that it doesn't matter so much what the core is made out of, but whether it has to have an atmosphere and its just general net rotation rate.
Okay.
Yeah, what
But
about
it
the
seems to be
moon?
dependent upon.
What about our moon?
Our moon has no atmosphere, and I think it rotates, relatively quickly. It has very little magnetic field. It has none, but it's very small.
Consider 27 days as a quick rotation.
Well, not that quick. But in any case, it doesn't have very much of a magnetic field. So it would have two strikes against it in that case.
I think
But my own.
I think that it
Well,
is not. I think that it is not so much related to rotation as to shape of these bodies. Of did you
they're all round.
think about some correlation between the shape of the ellipse? Earth has an ellipsoidal shape of. And more maybe this other has a more sharp like I am did you try to make a correlation with shape of these planets or and magnetic fields? I think it would be interesting.
All planets are generally very spherical. Maybe a little bit ellipsoid due to the rotation, but they're all spherical.
Earth is in fact ellipsoidal shape. I don't know. I think so.
Although
What about,
just as if you want to know what my speculation is on that, what I think is a thick atmosphere is necessary because you need to have a current flow. Basically, you need to wrap a wire around the planet in order to start the magnetic field, right? So in order to carry that electric current, you need an atmosphere that flows like a jet stream, like we have a jet stream that rotates around the Earth. That actually creates a current of air, of atmosphere that rotates around the entire Earth. Now, if you put some charges in there, like we have lots of charges in the atmosphere, we see lots of thunderstorms. There's a thunder strike on the Earth like every 5 seconds. So there is definitely a lot of charges up there. So you just get that charge to flow in one direction. That creates basic weak magnetic field. But now what that does is that charges the Earth's core, which is rotating. And then that is what causes the dynamo to actually spin up and create very large magnetic field. So the magnetic field is being generated by the internal iron core, as is convention, but is generally jumpstart jump-started and maintained by the atmospheric currents. That's my speculation. And that's why you need both rotation and thick atmosphere to get a strong magnetic planetary field.
You couldn't explain how a permanent magnet works, and so now you're going to tell me how the magnetic field of the Earth was created?
Yes.
How about
That's
the
my
sun?
explanation.
I don't know. It didn't convince me very much. So I would say that a permanent magnet has to have some kind of conductivity inside of it work, according to what you just said.
Now, yes, that's true, but remember that the best magnets are made out of non-conductors.
That was one of the things you started with by saying, yes. So I think you need to explain. I think you need to explain a permanent magnet first.
Well, we're short on time, so I'll give you the short answer. So the reason why I believe a permanent magnet works is because the little domains, the little grains, physical grains in the magnet, those are actually superconductive. That within the millions of atoms within a single grain must be able to form a superconductive loop inside that grain, which is a region, like that little picture of all the little grains in there. That must be basically a room temperature superconductor. And it's not a loop around any one atom, but it's a loop that goes around the crystal structure of the grain. So all you have to do is that when you put the magnetic field on it, it gets that superconductive loop going. Now, once you've got that going, that defines a magnet. And because this material is generally non-conductive,
once you remove the magnetic field, the effect goes away. So why does it stay there after you remove the magnetic field?
Well, if it's a superconductor, if it's a room temperature superconductor, that means
if I bring a magnet up to a superconductor, it creates supposedly a current in the superconductor, but when I remove the magnet, the current goes away.
Well, probably because this is not a conventional superconductor. All I mean by superconductivity is that once you get electric current running on the loop of this crystal, it keeps going. Now that may work differently from every other kind of superconductor that we know of. And this is why probably we haven't recognized that this is actually kind of a room temperature superconductor. That's only that a loop of current can do it. So, but that's my speculation, is that however you think that works, I mean, I can only speculate how that works, that there's a room temperature superconductor in each of these little specks. And the electron cannot escape from the speck because it's basically non-conducting, right? If the electron were able to escape and go to the next grain, then it couldn't basically get blocked and exert a physical force. So the electron, this is why I think magnets, the best magnets are made of non-conductors, because they have to restrain the electron within the grain. So within the grain, it's conductive, but it cannot flow outside the grain. And since it cannot flow inside the grain, all the electrons just can't all bunch up on one side of the magnet, and then that would certainly decrease its ability to exert a force. So this is how I explain how a permanent magnet works. It's just superconducting grains, you stick them together, that makes a magnet. That's the short story for how the permanent magnet works. It's just an electric loop. Ultimately, all magnetic fields are electric loops. And the permanent magnet just contains lots of small of these small electric superconducting loops. But you know, that's one possible speculation. Quite possibly, I think an experiment should be to determine, you know, start with that hypothesis and then use like these squid detectors, which are used to detect superconductivity, and see whether there's something in these permanent magnets that is room temperature superconductive. But otherwise, I don't really see how a permanent magnet can exert the fields unless there is an actual current looping. And I don't think it can be looping around the particular atom itself. I think there have been experiments showing that, you know, when they start with that hypothesis, that it's wrong, that it can't possibly be the electrons circling around the atoms that are causing it. And if that were the case, then you think there'd be a lot more ferromagnetic materials. Because another thing about magnetism, that only iron, cobalt, nickel are the only elements which are ferromagnetic. All the rest are not. And what's in common between those three? I mean, the only thing that's common is that the atomic weight is similar, or its size is similar. If it were the number of electrons looping outside the atom, then you'd think uranium would be magnetic because it's got more electrons and more free electrons to do that. But you know, uranium is not ferromagnetic, right? You'd think every element in the periodic table would be ferromagnetic because they all have electrons, but only iron, nickel, and cobalt, which suggests to me that it's a particular size, or that matters, for that at that particular size it is able to form whatever kind of crystal it needs to form these superconducting loops. And who knows how many atoms are involved in one of these grains? You know, maybe 1 million atoms are involved in these grains that make it superconductive. But once again, that's all speculation. But we're at the top of the hour here, so I think we're gonna have to try to summarize what we're talking about here. So let me go back to my notes here. No, that's not my notes. So we started out on a discussion of about how do magnetic fields work? And that basically we started from a position of, well, we have absolutely no idea how magnetic field works. We are basically completely mystified by, and I keep on sharing the right, mystified by the forces that we see. So I showed an experiment that shows the very, very basics of the force, the magnetic force, which is a wire which is deflected towards a permanent magnet, right? So we have the basic experiment with wire and magnet. So we're trying to explain, you know, why is that wire going towards the magnet? And this is the basis, this is the most basic magnetic field. And so the speculation is that electrons deflect towards magnetic fields by the Lorentz force law. Okay, so we know that we've got forces on moving electrons, and we see those in CRT screens, and that's why I brought that up. Now, given that we have that Lorentz force law and how they react in magnetic fields, you know, the question is, what happens to moving electrons in a wire? And they would still be subject to the Lorentz force law, which means that they will still deflect. And so the speculation is that the electrons still obey Lorentz force law. And if they basically hit the boundary of the wire, begin to exert their force on the bulk of the wire. So that was the basic speculation that we're trying to make here. And so when we look at that experiment of the wire and the permanent magnet, what you can kind of imagine in your mind is that you see all these like little electrons, like little bees flying through the wire. And when we turn on the magnetic field, or when they fly through the magnetic field, all these little bees are attracted to the magnet like they were honey, but since they are blocked by the bulk of the wire, we actually see the bulk of the wire move towards the magnet because all of these little bees attracted to the honey of the magnetic field. So as simple as that might be, I mean, this doesn't really, we haven't even touched what a magnetic field is. We haven't really touched too much what an electron is, although there's people who doubt what it is. But if we just accept what the Lorentz force law is telling us, and if we accept what the convention is for what wires are, which is electrons with moving current, I think if we just add those two together and accept that electrons flying in a wire being deflected towards a magnet are going to drag the bulk of the wire with it, that we can start to see the basis for the forces that are observed on a wire and at least a magnetic field. So hopefully we've made some kind of progress here. And but we still haven't explained, why is it an electron feels a force in a magnetic field, and why does it feel it at a 90-degree angle, which doesn't make any sense. So maybe we'll present that as a topic for next week, which is, this is getting one level lower, which is, why does an electron deflect in a magnetic field? I think we can understand why an electron deflects in an electrostatic field as just attraction of opposite charges. But what's going on with a magnetic field is there's no opposite charge in a magnetic field for the electron to react against, or is there? So perhaps that will be a discussion for next week, and can continue discussing how the magnetic field works. All right, but I think that will be it for today's discussion, and I thank everyone for participating. Now, if you have any thoughts about this, or if you would like to present anything about this, please keep it in mind and send me an email message if you have anything you'd like to particularly present. And we will see you next week then.